Hello, in this video I will be using computational methods such as the Newton-Raphson method and Broydens method to find the root of a variety of functions. The wider applications of these methods is that we can use them for a variety of optimization problems. So first I'll need to import the packages that we're going to need. So I'll need NumPy. We're also going to be plotting some of our functions. We'll make subplots. We're also going to be importing the JAX Python library, which we'll be using for performing automatic differentiation in the Broydens method calculations. Need to import SJNP. So now that we have all the packages we're going to need, I'm first going to explain the simplest method for finding the root of a function, which is the Newton-Raphson method. So the Newton-Raphson method is a simple iterative technique where we're basically assuming that the slope of the function between 2 points is a straight line. So for example, if we have the function y equals f of x, we make an estimate for the derivative of that function by using the slope between 2 points. So it's our simple y2 minus y1 over x2 minus x1 is our estimate for the derivative. So then if we know that we're trying to find the root of the function, that means that we're going to set f of x equal to 0. So in this case, we're setting y2 equal to 0. So if we plug in 0 for y2 and we rearrange our function, we can solve for the x2 for which y2 is 0. So once we get our estimate for x2, we can then plug x2 back into our formula for f of x and solve for our actual y function to see, or our actual y value, to see how close it is to our desired value of 0. And we can keep repeating that process until we get close enough to 0 that we have found the root of our function. So we can code out an example of this. We'll have our variable x be a list between 10 and negative 10 of 100 values. We can then define our function of x. We'll say for our function, it will be equal to x minus 3 times x plus 2 times x plus. We know in this case that our function will have 3 roots. Find the derivative of this function. Our values of x as using our f prime of x equals the slope, and we'll also need a dx. So this function, the function of x plus dx, x2 minus the function of x over dx will give us our derivative. And then we can define our Newton's method. Which for that, we'll need our function, we need our x, we need our dx, and we also need our tolerance, which we'll say is 1e to the negative 6. So as long as we're within 1 times 10 to the negative 6 of 0, we'll say that's close enough to be acceptable. So based on this, so this is our initial guess for x. So our new value of x be equal to our initial value of x minus the function at our initial value divided by the derivative of our function at our initial value and using dx. So once we have our new value of x1, want to reset it. So that's now our guess value. Let's try it now. We have our Newton's method function. Our initial guess, we'll use x equals 1. Dx, we'll say, is, actually, I'll just set it to a constant, so we'll make it 1 times 10 to the negative 5th. Okay, so a couple of things I missed the first time around. So actually, we want to update or reset our variable right at the beginning. So 1 is equal to our x0. Another detail we want is that we only want to iterate for a certain number of times. We don't want to be stuck in the loop forever, so we'll set our maximum number of iterations to 100. Another thing we need to consider is that we might iterate less than 100 times, but reach a value of y that is below the tolerance. So we want to make sure we exit the loop if that's the case. So absolute value of our y1, which we need to write code for, is less than the tolerance, and we want to break. And our y1, of course, is the value of the function at x1. So if this y1 is close enough to 0, then we don't need to iterate any more times. If that's not the case, then x1 will be equal to our new x1, our updated x1 will be equal to x1 minus our y1 value divided by the derivative of the function using x1 and dx. And then to return this, instead of just returning x1, we're going to return a dictionary. So we'll have n is equal to the function of x1, and x is equal to x1, and our number of iterations is equal to iter. So I forgot this needs to be inside a for loop. Okay, so that one. try it again. Okay, so let's try it. Okay, so let's try it again with an initial guess of 0. Okay, so we get our function -7 to the 10 to -13th, so it's pretty close to 0. We went through 5 iterations and x is about -2. So this is a good way to solve very simple functions where we just have one equation with one unknown. We can also use the Newton's method to solve a systems of equations, and for this we're going to use the Jacobian. And the Jacobian basically tells us the sensitivity of the function, so it's the partial derivatives of our functions for as they change with our x values, or with respect to our x values. So for example, if we have two functions with two unknowns, the Jacobian would be a matrix with our change in f with f1 with respect to x1 and x2, as well as our change in f with respect to x1 and x2. So if we're looking at the change in x, we can write this as delta x, which is the matrix of our change in our x1 for our first function and our x2 for our second function. And when we multiply the Jacobian and delta x together, we can get an approximation for the change in our functions. So for delta f1 and f2. And this is because the Jacobian is telling us that df over dx. So if you multiply df over dx times delta x, you get approximately the change in f. So once we have this Jacobian times delta x is approximately equal to delta f, which is also known as the secant function, we then want to bring our updated f value to 0. So basically we want our systems of functions to be a vector with all zeros. So in order to solve for our x value or x new, where our f new is 0, we want to take the secant function and multiply it by the inverse of the Jacobian. So then we can solve for x new. So we multiply j delta x by j inverse, and the Jacobian and the inverse Jacobian will then cancel out, and so we'll be left with our new x value is equal to the x old value minus the inverse Jacobian times our old value of our function. So if we want to code out what this would look like, we will first define our vector, which will contain our two functions. And for this, our x value, rather than using the NumPy line space, we're going to say it's equal to a one-dimensional array. And we'll use the same example function that we used in class. So we're now going to define a function for calculating our Jacobian. So for this, we'll need our function, we'll need initial guess for x, and then we use the same tolerance and dx values. To do that, we're going to start with size of our initial guess for x's. We'll set equal to n. So basically, if we had two values of x, then n would be equal to 2. So then we can say that Jacobian is a matrix and it'll be an n by n matrix. So again, if we had two functions with two unknowns, then our Jacobian will be a 2 by 2 matrix. And actually the syntax for that would be zeros because we have an empty matrix that we haven't filled in yet. So these should be flipped. So now we'll want to iterate through all of our values of x. So for I in first our x1 will set equal to x0. Means our initial value for our function will be the function at x0. Jacobian will be so our initial value for our function will be the value of a function at x0. So now that we've got our initial guess for x and our initial value of the function, I'm going to look for each value of our x values. So for this one, it will be for x equals 1 and x equals 2. We'll set x0 equal to our old x0 value plus dx. So then we can calculate the Jacobian as our new value function, or new function at our updated x value minus our original divided by dx, and then we can put x0 back to what it was before. So we're updating x, calculating the Jacobian, and then resetting our x guess value. And this will be for each of our and from this we're trying to get our Jacobian. So we have our function, we have our initial value of x, and we have our Jacobian. So now let's define our Newton So this will be similar to our one-dimensional Newton's method in that initial value of x, and then if y is close enough to 0, then we want to exit the loop. Also, this doesn't have to be 2 dimensions. It could be got iteration. So we don't break, so if we still need to update our x value, then j will equal to the Jacobian of the function, and x1, the new x1 will be equal to the old x1 minus we've got following our Newton-Raphson equation, the new x equals the old x minus the inverse Jacobian times our old value for y. So if we do this, then return same as binary with values you want. Run this. Let's try it with an initial guess of 0. Copied that exactly from the example. Let me try again. Okay, so after a little bit of troubleshooting, so it's giving us a value now. So when we used, my mistake was I was putting in just one value of x down here, and in the example problem from class, there were multiple values. So in real life, this would be like our function was had multiple variables. So yeah, I think this is working now. So our function we have for f1, we're pretty close to 0. F2, we're pretty close to 0. It took 5 iterations to get a result, and our values for x1 is about 0.8, and for x2 is about 0.16. So the Newton's-Raphson method is the simplest way that we can find the root of a function. However, there's several limitations to using the Newton-Raphson method. So the two main issues with using the Newton-Raphson method is that it takes a lot of computing power to recalculate the Jacobian every single time you iterate through the loop, and it also takes computing power to take the inverse of that Jacobian for each iteration. The other issue is that not only does recalculating the Jacobian for each iteration take up more power, but it also can lead to rounding error, because every time you calculate that Jacobian, you're losing some of the precision of your answer. So because of these limitations, a better method for calculating the root of functions is Broydens method. And that's because in Broydens method, we're only going to calculate the Jacobian and its inverse one time. And then we will, instead of recalculating the Jacobian with each iteration, we'll calculate a correction factor, which we can use for updating our original Jacobian with each iteration. So this will allow us to perform the same calculations with less computing power, and also we will get more accurate results because we won't have the same kind of rounding error. So the way that the Broydens method works is that we're going to start with the secant equation, which we found from Newton's method. So that the Jacobian times the delta x is approximately equal to delta f. So we can rewrite this as our jn minus 1, so our previous Jacobian, times xn, which is the updated x value, minus xn minus 1, is about equal to fn minus 1. So we're wanting this updated value for fn to be equal to 0. So if we plug that in, we can then get this equation, jn minus 1 times delta x plus fn minus 1 equals 0. But we know that for our first iteration, that's probably not what's going to happen. Instead of getting 0, we're probably going to get this equation equal to f of n, or f to the n. So if we combine these two equations, we can then cancel out this f of n value and this f of n minus 1 value, and we can get this equation here, where we have the change in our Jacobian times the change in x is about equal to our updated f value. So what can we do with this? Well, we know that if you take a vector that is perpendicular to the direction of a vector that you're looking at. So for example, if we take a vector perpendicular to our delta x vector, this would be going in the y direction then, so we have this vector y. Then the dot product of those two vectors will be equal to 0, because if your vector is looking at the change of x and you move in the y direction, then your x values aren't going to change. So because of this, we can also say that the transpose of our delta x matrix will also be equal to 0. So because delta x transpose dot product y will be equal to 0, we can also say that our change in our Jacobian, or the dot product of our change in Jacobian times this perpendicular vector will also be equal to 0. So again, we're saying the Jacobian is looking at the change in f in the x direction. So if you go in the y direction, your delta j won't actually change. So if we put these values into an equation, we can then say that our change in our Jacobian will be equal to our new f of n divided by our delta x. So essentially we're taking this equation and we're dividing by this delta x. So we're moving it over here so that we get delta j by itself. And then in order to get the matrices to line up correctly, we'll then multiply the top and bottom of this equation by the transpose of delta x. So if we rearrange this to put the old Jacobian on the other side and also rewrite our f of n in terms of delta f, we'll then get this Broyden update equation, which says that the new Jacobian is equal to the old Jacobian plus this fraction here. So this is better than what we had in the Newton's method because we now don't need to update the Jacobian each time we take an iteration. But this still isn't good enough because from our secant equation, or from our Newton's-Raphson equation, we know that in order to solve for the new value of x, we need to have the inverse of the Jacobian. So how can we get the Jacobian, a new Jacobian each time without having to take the inverse of our updated Jacobian with every iteration? Well, we can use this Sherwood-Morrison formula. So the general form of this formula is that it computes the inverse of the sum of an invertible matrix, in this case invertible matrix A, and the outer product of vectors u and v. So basically this says if we have this matrix A plus this outer product, which is uv, the transpose of uv, and we're trying to take an inverse of that, we can just use our old inverse of A and add this fraction here. So this allows us to calculate the new inverse of our new A without actually having to take the inverse of the new A that we calculated. So we can easily plug in our values from our Broyden's update equation here. So u is equal to this fraction, our v is equal to delta x, and then once we plug our values from our Broyden update equation into the Sherman-Morrison formula, we get this final equation, which tells us that the inverse of the new Jacobian, so what we were trying to solve for so that we can plug it into our x new equals x old minus the inverse of the Jacobian times f old. This is equal to the old Jacobian plus this big correction factor here. So overall, this equation here is referred to as the good Broyden's method, which we can use for solving a system of equations. Okay, so now we're going to write code for calculating or finding the root of a function of a system of equations using Broyden's method. So we're going to find our function. We'll need, again, the function, initial value of x. Our initial Jacobian, we don't have one yet, so we'll just put none, and then from our previous function we made tolerance, and so we've got tolerance, say the maximum number of iterations we want will be 100. Verbose, that just tells us what we want to print out while we're iterating our function. In this one, instead of specifying dx, we're going to specify our maximum and minimum bounds for x. So x min or x max will be infinity. X min will be negative infinity. And I've now switched over to using jax.numpy instead of numpy because we're going to be using jax to use the automatic differentiation feature of jax to automatically calculate our Jacobian the first time. So Jacobian will be equal to x. So the Jacobian of our function will be equal to Jax Jacobian of our function. That's in the case of j is none, so that'll be the first time. Otherwise, we just keep it as j. Jacobian will be jf of our function. So we're only going to calculate the Jacobian once. We're also only going to calculate the inverse of the Jacobian once. And the value of our function at x, our initial value for f. So now we have our initial values. So now we're going to enter the loop. So we'll do I in so so now we need to specify what our dx is going to be, since we didn't say what it was before. So normally our delta x we get from this secant function. So it's just we had delta x is just the delta f divided by, or here. So x new minus x old is just the delta, or is just the inverse of the Jacobian times f old. Inverse times f. So that's what the dx will normally be. But if we get close to our bounds, which in this case it's infinity and negative infinity, so we don't really have to worry about that. But if, for example, you were in a situation where the function you were looking at had smaller bounds, so for example, if you were trying to calculate mole fraction in a distillation column and your guesses for x had to be between 0 and 1, you would need to be able to specify that. So in that case, I want to say that Okay, so that's what our value for dx will normally be. However, if we get close to our bounds, whatever we've specified them for x min and x max, we're not going to want to take the full dx. We're going to want to take a smaller step so that we don't exit the bounds that we were given. So we're going to use a fraction. We're going to make dx a fraction of itself using this variable alpha. So basically our dx will try for each iteration if we're too close to the edges, instead of just being regular dx, it'll be dx times alpha. So we'll get a fraction of our normal dx. So how are we going to calculate alpha? Well, we'll need the maximum and minimum limits of our alpha value. In order to calculate alpha. So the maximum alpha will be the biggest value that, the smallest value for alpha, so that we don't go over the maximum value for x. So since we want to take a minimum, because if we don't use the minimum value of alpha needed, then for one of our values of x, we'll go over the maximum. So we want to use a minimum. So we're wanting to do the minimum so we're wanting to calculate alpha for when x plus dx is too big and when it goes over the maximum value of x. So if this is true, so we're here, so numpy where this is true, then we want to calculate alpha as difference between our x maximum and our x value divided by dx. So this will be our calculated value for alpha. So now instead of dx being just dx, it'll be x minus x over our previous dx. But it's possible that we don't need to do this because maybe we don't have a case where x plus dx is greater than the maximum. So if that's the case, then when we're calculating our dx try, we just want alpha to be equal to 1, so that we still just get dx. So that's the case if this is not true. We want to do the same for our minimum limits. So what's the smallest value of alpha needed to never go below the minimum possible value of x? So where would this be the case? This would be if x plus dx is less than the x minimum. And then we'll do the same thing. Instead of dx, we'll calculate this value of alpha. But if we don't go outside our limits, then we just want alpha to be 1. So we've calculated our alpha for not exceeding the minimum. We've calculated our alpha for not going below the maximum. So now whichever one of those alphas is smaller, we want to make sure we choose that one. Will give us our value for alpha. So now the question is, how close do we want to get to the limits that we gave our x min and x max before we stop iterating? So how small are we going to let alpha be if we keep making alpha smaller and smaller? How long do we want that to go? So we'll arbitrarily pick alpha. We'll pick 0.1 as our kind of. We don't need to go any smaller than that, so because we don't want to be iterating forever. So we have that our value for dx is going to be alpha times dx. So then this means that our updated value for x, rather than just being x plus dx, it'll be x plus dx, the dx that we're trying. And then from there, we can calculate our updated value for f of our xp value. So now we want to make sure that as we're calculating these alpha values that we're going in the right direction, meaning we actually are getting closer and closer to the root. So for this, we're going to use this d norm. So d norm is just the magnitude of a vector. So basically we have our fp, that's going to be a vector, and then we have our value of f, which is a vector. So I'm sorry, when we have a norm of a vector, that's the magnitude of the vector. D norm, we're saying, will be the difference between the norms of two vectors. So if we just calculate this updated value for fp, our d norm, we can say, is norm of our, so we have the norm of our new f, so the magnitude of our new fp, minus norm of our old f. So if this is positive, norm is greater than 0, then that would mean that our the magnitude of this vector is bigger than our previous one, which means that we're getting further away from the value that we wanted from the origin. So we need to make alpha smaller. So alpha will be half of the previous alpha. Otherwise, though, if we're going in the right direction, then we want to leave if loop, or that while loop, because we don't want to change alpha anymore. So if our alpha is too small and we're not getting to the value that we're wanting, we're not getting to 0, then this is indicative of that our Jacobian, which we're using to calculate dx, that just means that our Jacobian isn't right. So no matter how many times we iterate through here, updating x, we're not going to get to the value we want, so we need to reevaluate the Jacobian. So if alpha gets really small and we haven't gotten to the root, then we need to reevaluate j. So how do we update our j? Well, we're using our Broydens update equation. So we're actually not updating j directly, but we're updating the inverse of j. So we'll take the inverse of j. So it's the next day and continuing on with solving a system of equations using Broydens method. So we had defined our function for Broydens method. And oh, actually, I didn't give it a name. Broyden, I'll say Broyden 3 since that's what it was named in class. And we calculated our Jacobian automatically using jax.numpy. So then we set that equal to our Jacobian. We calculated the inverse for our Jacobian and also defined our function. In this for loop, we're iterating through to make sure that our dx isn't going to take us outside of our limits for our x-min and x-max, which in this case we have as negative infinity and infinity. So the value of alpha we will change in order to edit our dx try here, so that when we update x, we never go outside of our bounds. And we also are saying that if alpha gets too small, then this means that we need to recalculate our Jacobian. So we'll take the inverse and then update our Jacobian. With that said, so in the case that it's not too small, then we want to just do continue. Exit that loop. And then, so these are for cases where we're figuring out what our new dx try has to be. We're updating alpha. So once we get to an alpha that is satisfactory, we'll set dx equal to our dx try, because we know that that dx try will now stay within the bounds. And we can, instead of having this fp, we can just set that now equal to our value for our function, and the same with our value for x. And we can print our x and y values. And we also want to make sure that we don't keep iterating for longer than we have to. So if our value for f is close enough to, our value for f is close enough to 0, so meaning it's less than the tolerance. So if j and p if the absolute value of our function is less than the tolerance that we specified, then we want to exit the loop. So once we've done this, we're still going to use our Broydens update formula, and So, okay. Now that we have calculated f, we've gotten it sufficiently close to 0, so now we want to update our Jacobian. So we're going to use the same, or we're going to use the same formulas that we had up here. So we're going to set our u value, our v value, and then finally our value for our inverse Jacobian. So from the Sherman-Morrison method, we know that our u value would be so JMP will calculate that automatically. So our u So we're now going to plug our values in to the Sherman-Morrison formula, and for this we're going to have to adjust the dimensions on our variables. So we'll have this variable u that we expand be our value of function, and then v will set equal to our value dx delta x in our formula by the Jacobian, or sorry, the length of that vector. And then we can use our Sherman-Morrison formula with our Broydens values plugged in. So we get our new value for J inverse is equal to J inverse minus just multiplying matrix. Transpose of V, as we're referencing our equation, so the J inverse transpose delta x times u. We have the J inverse times u times v transpose times our inverse of our previous, and all that divided by 1 plus t So here we're literally just plugging in our values that we calculated in this function into our Broydens updated formula. So, or our Sherman-Morrison formula. So once we've done that plug and chug, basically, we'll return value of x and our value of f. All of this should be inside that for loop. Work. Oh, I'm gonna have to run all first. Here we have our function for Broydens method. So now if we want an example to try out this function and see if it works, the example that we're going to use is the Rosenbrock function, which I have down here. Yeah. So here's an example of a plot for the Rosenbrock function. So the standard form of it I have written out here. So fxy is a minus x squared plus v times y minus x squared. So an interesting thing to note here about this function is that we're looking at a multivariable function. So it's not just a function of f of x, but rather a function of x and y. So we can apply the Broydens method to multivariable optimization, which we'll show in a second. The standard form of the Rosenbrock function is using a equals 1 and b equals 100. So when looking at the Rosenbrock function, we're going to need to use a more advanced method such as Broydens method. We can't use, for example, Newton's method for finding the minimum of this function. Or another way to put that, we can't find where the derivative is equal to 0 very easily for this function because it's very flat, as we can see in the plot. So it's easy when you're iterating through this function to end up going in the wrong direction and getting an incorrect value, which means that when you're iterating through this function to find the minimum, you have to take very small steps. So the approach that will be taken for finding the optimal value of this function, so in this case we're looking for the minimum, is we're going to be using the idea of Lagrange multipliers. So the idea behind the Lagrange multipliers is that if you have a function that's f of xy, we can draw these contour lines for that function, which is basically saying for each of these lines, this is all of the value pairs of x and y that are equal to a certain value of f of xy. So for example, if this outer ring is D3, that's a constant. So all these pairs of xy values are equal to that same value. So if we have optimization without any constraints, we would just be looking at these contour lines of f of xy. However, if we're trying to do constrained optimization, then we'll also have this constraint function. So in this case, we're looking at g of x of y. And so in this graph, the optimal value of our f of x of y will be where the gradients of the contour line of f of x of y and the gradient of the constraint function are collinear. So to explain that, using equations. So let's say, for example, we're wanting to find the minimum of the Rosenbrock function, and we're using this inequality constraint, which is y is greater than 2x minus 1. So we're wanting to find the minimum of the Rosenbrock function, but only for cases where y is greater than 2x minus 1. So while the true minimum of the Rosenbrock function would be y and x are both equal to 1, in this case, that's not going to be what we observe because it has to also satisfy this constraint we're given. So when we're talking about the gradients of the contour lines and the constraint function, what we're saying basically is the gradient is the partial derivatives of whatever function we're looking at in the different directions. So for example, if we're looking at our Rosenbrock function f, the gradient of f will be this matrix of partial derivatives of x in the x and y directions. And the same thing goes for our gradient constraint function. So the way we're going to write our constraint function, because we're not just looking at an equality constraint, we're looking at an inequality constraint. That means that in order to write this as an equality equation, g of x will, instead of just being equal to y minus 2x plus 1, which because if you move y to the other side of this equation, you'll get y minus 2x plus 1 is greater than 0. That would be gx. But in order to make the inequality sign an equal sign, we're going to add what's called this slack variable. So basically what the slack variable will do is that since we're trying to get g of x to always be greater than this value right here, because y minus 2x plus 1 should always be greater than 0. We're adding this extra variable in here because that'll basically ensure that we're always in the region that satisfies this inequality. So this way we're able to use have an inequality constraint, but write our constraint function as an equation. So we have our gradient here in the x and y directions. So the idea is that at that optimal value that we're looking for, these gradients will be collinear. So they don't necessarily have to be equal, but we can say each of these partial derivatives, so for example, df over dx, will be proportional to dg over dx. And we can express this using this lambda, which is the Lagrange multiplier. So basically these two equations are showing that at our optimal value, the gradient of our contour line and the gradient of our constraint curve are collinear or parallel. So if we take these two equations, we have our delta f and delta g. We can combine these equations to form the Lagrangian. So to form the Lagrangian. And then we can write this. I should have included here. What is the Lagrangian? So once we have these equations for f our contour line and g our constraint function, we can then combine these using our Lagrange multiplier to find an equation for the Lagrangian. So basically, the idea here is that the Lagrangian is accounting for not only the fact that we're trying to minimize f, but we're also trying to account for this constraint. So because of this, when we write our gradient for our Lagrangian, not only are we looking for the Lagrangian to be the partial derivative of the Lagrangian in the x and y directions to be 0, but we also want the change in Lagrangian with respect to the Lagrange multiplier to be 0. Because the idea is that when the Lagrange multiplier is 0, we know that our constraint is satisfied. So if we want to illustrate this in code, we'll using the Rosenbrook function as an example. We'll first define a Rosen for x. And in this case, x isn't just one variable, but it's a vector with multiple variables. So in this case, we're going to have our x, our actual x value, a y value, the Lagrange multiplier, and our slack variable. So, okay, so first, for the Rosen function, we're just plugging in our equation that was supplied up here. So 1 minus x squared plus 100, 1 minus x squared squared. That will make the first value in our x vector our x value. Y can be the second value, so that'll be x1 minus x0 squared, all that squared. And so that's our function that we're trying to optimize. Okay, next thing. So now that we have our value for our Rosen function, so now we want to make sure we have our constraint. In this case, we're using our equation from up here for g of x and y. So looks like x1 y minus 2x plus 1 plus z squared. 1 plus x, or I mean x2, because that's our slack variable. And finally, do our function for our Lagrangian. So for this, just realizing I think this actually, I think that this maybe actually is supposed to be a minus sign. So our Lagrangian that will be equal to our Rosen function f minus, we have our Lagrange multiplier, that'll be the last value in our vector for x, and then times the constraint. So we'll have multiplier times constraint So now we've got our function, our value, or we defined our function for the Broydens function, our constraint function, and our Lagrange. So now if we're wanting to apply Broydens method to this optimization, we're going to, just as we did before, we're going to calculate our Jacobian. So, I'm sorry, we're going to calculate the gradient for our Lagrangian because we aren't actually trying to minimize our value of our Lagrangian. We're trying to get the gradient to go to 0 because that is when we will have our optimal value for our function f and also will be satisfying the constraint. So we're trying to find the root of our gradient of the Lagrangian. So we'll write our gradient of the Lagrangian as dl. And so we're going to use Jack's JIT, which will make the calculation go faster. And then inside that we have Jack's, and we're trying to find the gradient of L. Once we have that, so we'll need, as always, we'll need our initial guess for x. So for this, I'll use the same examples that we used in class. So that was 0.1 for our initial x and y values, then 10 for our initial slack variable, and 1 for our initial Lagrange multiplier. And then once we have that, so we're trying to find our value of x and our value of f, for x being all those values we were looking for. So x value, y value, slack variable, and the Lagrange multiplier. And so now we're going to plug in our function Broydens 3. And our inputs for that will be our, not the formula for the Lagrange, but the gradient of the Lagrange, our initial x value. Finally, we'll specify our max iterations to be 500. So let's see. Got it to run. So now that it's running, we can print we want to look at what our value of x was, and we also want to look at what our minimum value of the Rosenbrock function was at that value when we're satisfying that constraint. Okay, so now we've printed our x, so we have our x value, y value, our value for the select variable, and our Lagrange, and we can see that our minimum value for the Rosenbrock function when we're satisfying this constraint is about 2.27. So this has been a demonstration of how we can use computational methods to find the root of otherwise difficult to optimize functions. And the wider applications of these kind of computational methods would be when you're, for example, designing a chemical process and you wanted to look at what's the optimal sizing for a certain vessel or a reactor. You can use these computational methods to find what your optimal conditions would be. So this can be useful in a variety of applications.